Okay, so my name is Casey Chamberlain, and I'm going to be talking today about optimal strategies for sustainable woody biofuel harvest. This is a project I worked on with Christy Sullivan and Steve Morelli and the Cornell Department of Natural Resources. Before I get started, I'd just like to thank them so much for all their help along the way, helping me get this project together. Also like to thank Christina Chin, Gary Goff, Cassie Garcia, Devin McMahon, and Peter Smallage for the help along the way as well. So with the growing, a demand for energy and also the depletion of fossil fuel resources, many people are now looking towards alternative sources of energy, specifically ones that are renewable. One that's starting to get a lot more attention nowadays is woody biofuels. And this one is a particular concern to us in New York State because, as you can see in this picture on the bottom left, New York State is approximately 2/3 forested, so it would take a big toll on us. So what traditionally happens when a forest thinning occurs is the loggers come in, mark the trees, and then on the bottom left, you can see that bottom right, sorry, they take those pieces of sawtimber, those the thick parts of the tree. And what happens is most of the time, things that are at the top of the tree, what we're going to call 4-inch material, that's 4 inches in diameter and less. The tops, the twigs, branches, etc., is often left on the ground and just left there. And sometimes also, 10-inch material that is diameter of the tree 10 inches and less is left on the ground as well. But recently, with this sort of demand, as I was saying before, for alternative energy sources and the advent of these new technologies, the Hogzilla and all that, a lot of this previously discarded or left on the ground wood is being chipped up and turned into fuel. So now we have the three options available to us. To the top left is just take that main log out and leave a lot of material on the ground. On the right is just leaving a little bit, so just that 4-inch material. And then the bottom left is what's starting to happen more and more nowadays is that's removing everything and leaving the floor a little bit more empty. So what we wanted to look at is, are there ecological benefits to leaving this woody material on the forest floor? And if so, is there some sort of tipping point where the removal makes the environment no longer sustainable? So we want to look at microclimate effects, biodiversity, and forest regeneration. So our main objective was, stated simply, to determine whether woody material left on the forest floor positively impacts forest ecosystem processes. And more specifically, does it have an effect on soil moisture and temperature as measures of microclimate, salmon abundance as a proxy for biodiversity, and seedling growth as a measure of forest regeneration. So we had 3 study sites in central New York. 2 were located in Mount Pleasant, which is just outside of Ithaca. That's the circle on the top right. And 1 was located at the Arnott Forest, which is the one at the bottom left, which is where I was staying for most of the summer in a cabin. At each of the 3 sites, we set up 3 different treatments. We call 10-inch, 4-inch, and whole tree. In the 10-inch, we left all the material that was 10 inches in diameter and less on the ground. The 4-inch, we left all the material that was 4 inches in diameter and less on the ground. And then the whole tree was clearly removing the whole tree. Each of the 3 plots were set up in 1.5 hectares each, and they were set up in close proximity to each other. Typically around 30 to 50 meters apart, but all in the same area. And this setup, shown on the screen here, was done at each of the 3 sites. When the cutting occurred, the trees were cut so that in the treatments with piles, 10-inch, 4-inch, the trees sort of formed loosely consolidated piles, and these were geographically distributed throughout the sites. And also for each pile that was made, a subsequent paired open site was determined no further than 5 meters away. And this was so that we could do pairwise comparisons for piles and no piles. So our first measurement was temperature. We used Hobo brand temperature loggers that we placed in pairs, in piles and not in piles. We had 90 total that were out, and they recorded the temperature every 4 hours throughout the entire summer. Another microclimate measure we did was soil moisture, and this was also done in paired measurements. We used a volumetric water content meter, or soil moisture meter, sorry, that measured volumetric water content of the soil. And whenever we did a measurement in the pile, which is the image on the left, we did a measurement in the open site that was paired with it, which is seen on the right. For our measurement of biodiversity, we did salamander transects. What we did is we set up transects of 50 meters long and 3 meters wide, which we walked along and flipped over every rock, stick, and piece of bark that was there, measured how many we flipped and how many salamanders we found. And these were always done at each of the 3 different treatments, 10-inch, 4-inch, and poultry, within a short period of time of one another in order to compare those as well. And lastly, we did vegetation surveys to measure forestry growth. This was another paired measurement. So whenever we did a pile, we did its subsequent open site as well. What we did is we just simply went around the pile and its open pair and recorded the types of species we found and how many there were over 1 meter and 2 meters as well. So under results, right here is an example of one of those pairs of temperature loggers that were placed in the pile and its open site. The y-axis shows the temperature in Celsius, and the x-axis shows the date as it goes throughout the summer, starting in June, ending in October. The red line is the logger at the open site, and the black line is the logger inside the pile. This right here is just one example of one. And I said there were 90 data loggers that were placed around, and they all shared this similar pattern. You can see that the open is consistently hotter than the pile, but also it's important to note that the extremes are much higher as well. Compiling all those measurements of temperature into one box plot, we found that this is just for noon, by the way. Just it's a good way of measuring the peak of the day. We saw that the mean open temperature was much higher than the mean temperature in the pile, but the maximum temperature was also much higher than the maximum temperature in the pile. Where the pile got up to 31.5, the open got all the way up to 35.7 degrees Celsius at some points. In running a general linear model of statistical significance on these values, we found that there was a highly statistically significant difference between the temperatures in the open sites and the temperatures in the piles. Because we measured these values in pairs, it set up nicely for doing paired t-tests. So running paired t-tests on noon temperatures, daytime temperatures, and all of the data, even those at night where we thought the effects might be mitigated, we found that no matter how we looked at the data, it was a highly statistically significant difference between the open and the pile, and that difference was that the open sites were always warmer. This was also true on a treatment level. Looking at, again, noon, daytime, and all data for 10-inch, 4-inch, and poultry. No matter how we looked at it, we found that 10-inch was cooler than 4-inch, which was cooler than poultry. And again, these were highly statistically significant differences. The second microclimate effect was soil moisture. We're going to start looking at what we call a week in the life of a pile. What we did is for 4 days in a row, during a period with no precipitation, we measured the same 12 piles and their subsequent and their open pairs for 4 days in a row and tracked their changes. Right here is just one representative example. On the y-axis is volumetric water content, and then on the x-axis is throughout the week, 4 days. You can see that on the blue line is the pile, where the red line is the open. You see that the pile is higher the entire time, so wetter, and also that the difference between the two gets larger as the days go on, showing that the piles capture the water but also retain the water better than the open sites do. Here's another example. You can see, again, the same trend, 6.1% greater at the beginning, whereas it's 9% greater at the end. And then 4 more examples here, again, showing that same similar trend where the pile is always higher, always wetter than the open, and also that how that difference increases, sometimes up to 16.9. So again, whenever we measured volumetric water content, we measured the pile, the open site, and then we took a difference. This graph here shows that the difference between the two values. Anytime, so the y-axis is the difference in volumetric water content between the pile and the open, so pile minus open, and the x-axis is just each different point. So whenever the point is above the thick black line, it means that the pile was wetter than the open. And whenever the point is below the thick black line, it means that the open was wetter than the pile. As I pointed out, you can see that there are only 8 times when the open was wetter than the pile out of 92 total samples. And all of those times when the open was wetter, it was very, very slightly so, never more than 5%. Whereas when the pile was wetter, it sometimes got up to over 20% greater and was almost most consistently over 5. So if we measure biodiversity, say we have salamanders abundance. This graph shows sort of what we call the search effort per salamander. Basically, the measurement on the y-axis is how many objects we had to turn before we found a salamander. And you can see that in the whole tree, it was much harder to find salamanders. We had to clip almost 50 objects before we would find one, whereas in the treatments with the wood on the ground, it was much less, around 20 flips. And then for forest regeneration, we looked at those vegetation surveys. In piles, we found that there was both more overall species, or more overall seedlings, and also more types of species than there were in the open. And again, looking at this on a overall treatment level, we again found that treatments that did have wood on the ground, so both the 4-inch and 10-inch, had higher seedling densities and species richness than the site without any wood on the ground, the whole tree. So looking at all this data, we determined that wood really does matter. Wood matters for microclimate in mitigating temperature maxes and variability, and also capturing and retaining soil moisture. Wood matters for biodiversity. It creates a complex structural environment for salamanders to live, and also aids in those microclimate effects that help for them as well. And wood matters for forest regeneration. It matters for seedling survival and growth, seedling abundance, and tree species diversity. So our final conclusion was that wood matters for microclimate, for biodiversity, and it may be essential for forest regeneration. Thank you so much for listening.